Hello, class. So we are going to introduce to you how to do complex power calculation. So in this case, we're going to have the voltage and impedance is given. So in this case, so in our last video, I showed you I gave you the V and then I gave you the I. So we compute for the complex power, okay? So in this case, we're going to demonstrate that we gave you the V and then we gave you the impedance, okay? So let me put the impedance there. To save some time, I'm just going to copy them in. So this time I gave you the impedance. So you can see that instead of giving you only one value, I gave you 24-hour value. This is because usually we compute the current change for the house for a 24 period of time. So this would be a vector that have 24 values in there. You can either import them from an Excel spreadsheet. I'll talk about that in our later demonstration, or you can just directly put the value here in this main script. So you can see that this is 1, 2, 3, 4, 5, 6. So I'll have 6 value here. So that's from 1 o'clock from midnight to 6. And this is 1, 2, 3, 4, 5, 6. So this will be from 7 to 12. 1, 2, 3, 4, 5, 6. So this would be from 1 o'clock to 6 p.m. And then this 1, 2, 3, 4, 5, 6, 7. Okay, so let's delete this one. So this would be from 7 o'clock to midnight. Okay, so we can just pick a 24-hour load so we can compute for 24 current. Okay, so if we run that, you'll see that for the Z RMS, I have 24 value to start with. So you can see that I use 24 times 1, so that means it has 24 columns and only 1 row. So this is a vector. So we usually write them in a vector format, okay, instead of 1 times 24. So for the for this impedance, we can have an angle as well. So this shows that this impedance is either capacitive or inductive or resistive, okay? So normally we use voltage as a reference. So I'll change this back to 0. So later on, we can change this to another value because in reality, when you have a generator here, you're supplying load, you have a transmission line, and then here you may have a distribution transformer. And then this will be your house, okay? Our load will be right here. So this could be a resistor, or it could be an inductor, and then a resistor here. Or this could be a capacitor, and then a resistor here. So either way, you will have a number of impedance that serving in parallel, right? This is your household. So this kind of a load can either be, suppose this is your, you have a water heater, it's made a resistive load. And then if you have for example, a fan, like a ventilation fan, then it would normally be a motor load, but the winding has some resistance, so it could be like that, okay? Most of the time, we don't really have capacitive load in our household because we usually just have motors, and then we don't have capacitors running in our household, okay? So in this case, oftentimes our theta here, this angle is positive, because if it's positive, then it will be, say, 3 plus, say, 5J, that kind of thing. So this is inductive load, okay? So then let me just start to write that. So in this case, we selected an angle of 30 degrees, and then our time, because we're going to compute later on for 24 values. So our T will be from 1 to 24 hours. So this will be from the midnight to middle the next day, okay? And then we were going to compute it for the current. Because we have a 24 value to start with, so we need to have a loop. That will be from the first time slot until the 24 hour. So you can put either length t here or directly just put 24 here because you already know the length of the time vector, okay? Otherwise, you can just say, hey, what is the length of t? I will just iterate it from 1 to 24. So if usually if you have this step size as 1, you can just simply write 1 over 24. If there's a 2 interval, like from 1, the next hour would be 3 o'clock, then you will have a time step of 2 hours, then you have to put 2 here. But here we just advance 1 hour at a time, so we can do that. And then usually this for loop, when you tap in for, it'll give you the end. So this would, anything in between will be looped through, okay? So let's do one thing. So before we do the loop, we can, since we already have the z, I'm going to just print out what this z value is. Let me just make a section break. I'll just see what's the first value of z. Let you just briefly see that. So you can see that this shows us the load impedance is this much, okay? So this means that I have this RMS value times cosine plus the sine times j. So your real part resistance is 21.65, and then your inductance, the reactance of it is 12.5 j. So this is for hour 1, okay? Because each hour this z value is changing, so we really need to just put this in here. So each time this is no longer 1 because we want to let it iterate, right? Iterate the if the first iteration is 1, the second it will be advanced to 2. So this is why we use a for loop for it, okay? And then we can see we calculate the z value, and then we can also compute for the I next, okay? So I will equals to v divided by z, okay? And then the IRMS simply equals to ABS I. This is because I, when computed this way, this is a complex number, V is a complex number, Z is a complex number. So this I is a complex number. If I want to know the RMS value, I need to calculate ABS. ABS computed the magnitude that basically compute the real part, the I real part square plus the I imaginary part square. So this will be the ABS value, okay? And then I'm going to see I angle equals to RAD 2 degree angle I. So angle is a function. This function will give us, if I is a complex number, then using angle I, it will return a angle for this complex number. But this angle will be in radius. So if we want to see the degree of it, we need to use this function, radius to degree, okay? So by doing that, I know the current magnitude, the RMS value of it, and then I will compute for the angle in degree, okay? So once I have that, I can print this out. Okay. So here you can see that this angle, also I do this angle, I. Okay, so this will let me just show you more clearly. That's the first time when we do the debugging, we don't want to let it run 24 times. We just want it to run one time. Okay, let's see what happened. This value. Oh, this should be RMS instead of RM. Okay, let's run that again. So you can see that here is a few tricks. You can see that I printed out here this angle sign, and then this degree sign. How did I do that? So you can see from here, you can see this is float number for this variable. This is the RMS value of I, and this is a float number, and then this will print out the angle. So here, this is a Unicode for this value, okay? And then this xb0 / xb0 is a Unicode for degree. So if you want to print out some special symbols, you can just go online and check what's the Unicode of the symbol. Then you can just put them in this printf format. It can be printed out. This is very good for you to print out result. Okay. Close that. So after we do that, we can just compute for the I value. So the next thing that we want to do is to compute for the complex power, right? So before that, we can do the power factor. So power factor should equals to cosine B angle minus I angle. Okay. So here I compute everything in degree. So you just if you are used to degree, you just use a degree all through, and then you use cosine D. But if you're used to radians, then you use radians all the way through. Otherwise, you will likely to make a mistake. Okay. So now we're computing the power factor of it, and then this power factor simply will be this angle, and then the voltage angle minus the current angle, because this angle is for the I iteration. So you put I here, okay? So your power factor here, you should put an I here. So then for each time slot, like 1 o'clock, 2 o'clock, 3 o'clock, you will compute one value for power factor, and then one value for the current magnitude and angle, okay? So after this, we can compute for S equals to B times conjugate of I, similar to last time, okay? So this will print out the power value of it. You can see the power factor is 0.866, and then the power, the complex power is real power plus reactive power, okay? So again, we can print out this by saying, okay, print out the power factor, and then print out the power value. So in this case, you need to remember here, you need to put an I here, because otherwise it will become a matrix. You cannot use this to plot out a matrix because there are multiple numbers in PF. Same thing here. I need to put an I here. So this would be let me clean the up a little bit. Okay. So this way, let me run that. So now you can see that we computed the power factor, and then we computed the complex power. But here, because the complex power, I print out the ABS value, so that's the magnitude. Okay, so we should say the magnitude of the complex number. is complex power is that. Otherwise, you need to print out using this type of command, so you can plot out the complex number. For example, let me put it here just to give you an example. If you want to plot out the complex power in complex number, then the complex power is, then you can say, hey, this is the real part of S, and then the imaginary part of S. Okay, so you can see the difference here. Now you can see the complex power is in this real and real part and reactive part. Okay, or you can just print out the magnitude, which is the ABS value of that. Okay, so once you do that, obviously our P, usually P is the one that we're caring about, because in your household you pay for the real power you consume. So that's just the real part of S. And then your QI simply will be imaginary part of S. Okay. So that case, I will run it. You'll see that the P equals the real part, and then Q equals the react power part. So we already mentioned that last time. So the other thing you can do is you can actually compute the P by doing this. This is also okay. I'm going to show you an alternative way of doing that. You can use the current magnitude, the square of it times R. That will be our real power, or you can use the magnitude of I, because you remember when we mentioned that for a sine wave, it can be equivalent to the DC, right? So similarly, a sine wave of I can be equivalent to a DCI. So when you compute the power consumed, you can think of this value as just using absolute value times x, the square of I, and then times this x load, and then that will give you the react power and then real power. Okay, so let's see if that's the give us the same value. Okay, so the R here, I haven't defined that. This is because the R equals to the real part of Z, okay? And then the X load equals to the imaginary part of Z. Okay, so you can see that both will give you the right, correct amount, okay? So normally this is more straightforward. So usually when I compute for P, I just compute for the current, and then I use V times the conjugate part of I, and then I take the real part of this complex power, I get the real power. And then I can take the imaginary part of the complex power, get the reactive power. But there are alternative ways of computing the real and the reactive power, just so you know that. Okay, so let me just comment those out. So this will complete one iteration. So if I want to do, say, from 1 to 5, then when I run this, so if I run this whole thing, then you see that put I here. Yeah, this is the part that you need to pay attention, because when we run this multiple times, so all these variables, they are a matrix. They are no longer a single number, right? So we want to put here I, okay? So in the end, when we do this computing, we need to put all the I here. I don't have to. So this way, then you would be able to compute, save the p-value for each time interval, okay? So if you use I, then you use I consistently, then this will be an intermittent value. So at the beginning of the next iteration, when they run through here, this value will be erased. It will be a value that won't be saved. But if you have a IRMS I here, then this value will be saved in this vector format, okay? So you can see that if I run that, you can see that the output here is too messy. This is because I output all these numbers all the time. So if you use a for loop, then you want to put a semicolon here. So the input, the output to the screen will be suppressed, okay? So when you do that, you do this, and then you put a semicolon here, then you run it. Then you can see that it will only print out these print values for each interval. But even this is cumbersome because we don't really need to print this out for all the time interval, because it's already have been saved in this RMS value. You see here, this already been saved in this vector, okay? So I no longer need to have this intermittent value. So normally when you do a for loop, you comment out these print command. So why we still need that? This is for debugging purpose. As I said at the beginning, I don't want to run it from the first to the 24-hour. I only want to run 1 hour to see if there's a problem in the code. And then once this passed, then I start to, okay, say run 24 hours. So in this case, I want to comment out all these intermittent results. Okay, so now I run it. Let's see what is, oh, yeah. Yeah, the debugging usually takes some time. So now only the power factor is output here. So that's something I forgot to comment out. Impedance. Comment out, commented out. Oh yeah, this is the one I haven't commented out. So control R, if you hit control and R, that'll comment the whole sentence out. Or you can just put a sign here. It'll comment this whole sentence out as well. So once I have that, since we no longer have this intermittent result, so what should we do? Okay, we can add in another section. Okay, so we can print out them in the figure. So figure is the most compelling visual aid for you to see what is going on, right? So I can plot out. Say usually the RMS value is the one that we're interested in, right? So we plot this, and then our X label or someplace B current time of the day, and then our Y label. Someplace B, load, and then it's in apps. Okay, so when we print this out, we run, you can see that it'll print out the current. So you can see the current is this is a night. We are sleeping, so the current is low. We have a low consumption, and then in the morning when we wake up, suppose this is in winter, we turn on our space heating unit, and then we are doing the cooking, so the load suddenly jumped. And then when we all go to school, this consumption would drop. You just have a little bit the HVAC load, the space heating load. And then when you return home at night, at 5 o'clock, start to do cooking, and then watch TV, and then you later on you fall asleep. So this will go back again. So this will follow a realistic load consumption curve for a household. Okay. So you can see that in this case, we can also plot out the a better practice usually is you put the T here and then plot out the T. And the other thing we're interested in is P, right? The power consumption. So we can copy this. You will see that the power consumption will follow more or less the same load shape, right? This will be power. It will be actually real power. So real power will be in watts. Okay. And then we can also do the same thing for, let me plot out in figure 2. And then suppose I want to plot them out in one plot as a subplot 2, 1, 1. And then plot the reactive power into subplot 2, 1, 2. Okay. So this will be my Q. This will be my reactive power. So that will be in VAR. Okay. So this way we can plot out all the results for 24 hours. Let's see here. See, this is our real power. This is our reactive power. So if you want to have the title of it, you can just put down title. This is real power. And then the second one is the reactive power consumption. Yeah. Reactive power consumption. So now I run it. You can see that you have the title here. So when you are doing the homework or a project that you can plot out a figure like this, and then you need to label them. See, this is the X label, and then this would be the Y label. Usually in scientific studies or when you're doing a report for your clients, you need to have the figure properly labeled, okay? And then you can see this is the load current. One thing that I said we